Hello and welcome to the future of being human unplugged, the place where we have conversations that I'm sure you'll find it very hard to have anywhere else. My name's Andrew Maynard. I'm a professor of advanced technology transitions at Arizona State University. I'm also the director of ASU's Future of Being Human initiative, and I will be your host for today's broadcast. So, I should say up front that today's conversation is going to be about as unplugged as it gets. And as you'll probably know, the focus is on artificial intelligence and cooperation science. I'm being joined by two very good friends and experts in their respective fields who, I must confess, until just a few minutes ago had never met. And this was intentional. And it was intentional because I think this is going to make it a very, very intriguing conversation. But what makes it even more interesting is that these two guests come from two very different backgrounds and perspectives. Of course, doing this could be a recipe for disaster, but knowing Athena and Mark, and I'll introduce them in a second, my money is on us having a conversation that'll keep you riveted to your screen, as we probably do go places you never imagined, and probably places I'm not imagining at the moment. Before I introduce both of them, though, I should set the scene. In our last Unplugged broadcast, we touched a little on the intersection between the science of cooperation and AI. If you saw that conversation, and it's actually still available on the Future of Being Human YouTube channel, you'll know that we explored the tensions between an AI future where humans and machines cooperate, and one where AI evolves to be, in a somewhat dystopian future, parasitic on humankind. Despite that rather disturbing vision, we're actually finding there's growing interest in how the field of cooperation science might actually inform and guide our understanding of human-machine interactions in the future, and even machine-machine interactions in very positive ways. And after the last broadcast, I wanted to explore this further. So I thought I'd throw together the most interesting cooperation scientist I know with the most creative AI and neuroscience expert I know, and sit back and watch the sparks fly. So now both of my guests know exactly what I'm expecting of them. So without further ado, let me introduce you to my two guests for today. And for those of you who have watched previous Unplugged broadcasts, you'll know that neither of them are a stranger to this broadcast. So let me just bring Athena in here. So, hi, Athena. First of all, we have Professor Athena Aktipis. Athena is...
You can just call me Athena.
It's going to be Professor Athena all the way, you realize now. So, Athena is an associate professor in the Department of Psychology at Arizona State University. She's also co-director of the Cooperation Science Network and the Human Generosity Project. Athena studies cooperation across multiple systems, which I find absolutely intriguing, as they range from human sharing to cancer and even kombucha. She's also a leading expert, or she is a leading expert in the field of cooperation science more broadly. I would also say that Athena is a wildly creative academic, and as we discovered as we were talking before this show, a very funny academic as well, with... I had to throw that in, with an unhealthy interest in zombies. And although crazy as that seems, it's actually very serious, because she studies what the concept of zombification can teach us about ourselves and the world we live in. Athena's the brains behind Zombified Media and the Zombified podcast, which you should check out anywhere that you get podcasts. She's also the author of the upcoming book, A Field Guide to the Apocalypse, a mostly serious guide to surviving our wild times. And Athena, remind us when that hits the shelves.
April, so just
April.
A few months away.
Get your orders in. And then joining Athena, I have Professor Mark Daley. So Mark is the Chief AI Officer at Western University in Canada. He's also a full professor in the Department of Computer Science at Western, with cross appointments in 5 other departments, including the Rotman Institute of Philosophy and the Western Institute for Neuroscience. And I love, Mark, the fact that you combine both AI and the computer science side of things with neuroscience, which I think is going to make this conversation particularly special. Mark's also a faculty affiliate of Toronto's Vector Institute for Artificial Intelligence. But despite all of that stuff, the real reason he's here is that he's a fiercely creative academic who always impresses and wows me with his ability to think creatively beyond the obvious. So Mark and Athena, welcome to the show, or welcome back to the show.
Well, I'm nervous now. You've set the expectation.
You're going to be great. So I should start by saying I have no idea where this conversation is going to go, but that is, of course, the beauty of the Unplugged format. But I do have a starting point, and I'm going to start with you, Mark, because I know that this is stuff you think about a lot. Can you just share a little bit about your speculations of where you think AI might be going? And I won't set a time frame. I'll let you set the time frame, whether it's the next sort of year, few years, decades, or whatever. But also tell us something about how you think these ideas around cooperation might actually be relevant to where you see it going.
Okay, so I'll give you my standard answer to the first part of the question. Imagine we go back to ancient Greece. Best mode of transport that we have is a horse-drawn vehicle. And now we skip forward 2 millennia to the 18th century, and the best mode of transport we have is a slightly better horse-drawn vehicle. 2,000 years. But then we skip forward just 200 years, and there's humans on the moon. That's more than a slightly better horse-drawn vehicle. And so, looking at just the next 20 years, I would be awfully arrogant to suppose that I can predict the moon landing as an ancient Greek, and that's what you're asking me to do. So the answer is I really don't know. And the time scale for generative AI right now looks like it's relatively short. So it looks like we're in the knee of an exponential growth curve, and of course this could plateau at any point. There's no guarantees, and that's why it's so difficult to predict. But for the moment, it looks like we're going to continue to be able to build on the models we've got right now, and there may be exciting breakthroughs that allow us to do things that aren't currently accessible. But let's talk about what is currently accessible. It's not an accident that so many corporations are marketing their AI as an assistant. Mm-hmm. ChatGPT is an assistant. Bing is an assistant. Microsoft has integrated GPT-4 into the Office suite as assistants. And so it's very natural for this pseudo-anthropomorphized conversational interface to, for us to immediately want to interact with it as if it's an assistant. And it's a role it's well suited to play. So I think we've actually set ourselves up for collaboration as the default in interaction with this technology.
Yeah, just push that a little bit further, because of course, if we're looking at a digital assistant, and for those that are old enough, I guess we've got to bring in Clippy, sort of one of the original ones that failed miserably from Microsoft. But it doesn't feel as if it's really a collaboration or cooperation if it's just a digital assistant. I'm assuming.
I mean, it's kind of one way, right? It's like,
right.
So if you're being helped, but is it really cooperation or collaboration if it is just a one-way interaction with one entity serving another, right?
But I'm wondering, Mark, sort of then within your vision, whether you see this as an assistant that maybe can push back and maybe sort of have a life of its own is the wrong way of looking at it, but something there.
It already is. So if you're using ChatGPT or Bing like Google, or the search engine, you're using it wrong. The whole breakthrough here is the conversational aspect. You can iterate, you can go back and forth. I have it edit my grants for me, and not just for grammar, but for content. Like, that whole section 2 is really weak. I didn't like the following 10 points, and some of them are throwaway, but some of them are pretty good. And so it is actually much, if you're using it right, it's much more of a partnership. And I haven't even touched the fact that there's this whole field of agentic LLMs now, where there are networks of LLMs interacting with each other and humans at some point in the chain too.
So, Athena, I mean, so this feels, especially when you're looking at those sort of clusters of LLMs that are sort of working with each other, this feels or begins to feel like some of the systems that you study from a cooperation perspective.
Well, yeah, I mean, they're just computational entities that are, interfacing with each other, I guess, right? To accomplish goals.
You say that so dismissively.
I'm sorry. Oh, I mean, no, I don't mean it to be dismissive. I'm honestly just like trying to wrap my head around, like, I mean, if you have these entities that, we do like sort of, I mean, because we've been networking entities together for a long time computationally, right, to get more power. I guess what's different when they start doing it with the large language models as their means of communication, and maybe also part of, like, I mean, obviously that's a computational structure that they're using, but does that help a lot, right, to like make for better computation if they're using the large language models as the method of computation and the method of communication?
But I'm also interested, actually, I'm going to come back to you, Mark, with this, because I'm intrigued with this idea of networks of LLMs or foundation models. I mean, is there a possibility, or are we already there, where they have their own degree of cooperation, which is independent of human interference? Are we actually developing true cooperative networks and ecosystems?
Yes. So shortly after ChatGPT came out, we had the LLM explosion. There was a package called AutoGPT that allowed you to network LLMs together, and they could call each other. And people got very, very excited, and it turned out to be a much harder problem to solve than we thought. Because unlike past instances where we network lots of compute together, but that was all engineered and we had fine-grained control over everything. Once you start using LLMs, you give up a lot of control. Right. And so one of the observations was LLMs can be lazy because they learned from us. And so you would ask the LLM to do something, you would say, oh, sure. And then it just would spawn a sub-process to go do that. And then that would happen ad infinitum. No one actually wanted to do the work, just pass it on down the chain. But progress has been made. A really immediate example of this is if you have ChatGPT and you ask it to generate an image, it is actually interacting with an LLM that's front end to Daley, and they pass messages back and forth in English.
Yeah, I find this so fascinating that we're already we're there, at least sort of in the context that you described. Athena, coming back to you, how similar does this sound to some of the biological systems that you study? I mean, and I was intrigued by the laziness comment, because surely that's part and parcel of cooperation or uncooperation.
Yeah. Well, I mean, if you can, fulfill whatever obligations or get whatever goal accomplished doing less, right? Evolution's going to favor that over doing more. But to me, the big question is sort of where are the goals coming from, right? Because when we're talking about biological evolutionary systems, we'll use what's called like the adaptationist kind of perspective, where we say, okay, we have these organisms, they have these design features. And so this probably means that, they're trying to accomplish these kinds of goals. And the reasons for those sub goals are because they're probably, increasing the survival or the reproduction of those organisms in one way or another. When it comes to, computational entities that are not evolving in the same way, right? They're changing, they're being influenced by their learning, by their programming, all of that. We kind of build the goals in directly and indirectly. And so in theory, it should be much easier to get cooperation, right? If you can say, hey,
okay. Sorry, actually, I've got to ask you this then before I go back to Mark. can you program in cooperation? Are there a set of rules there where we could say we could study kombucha? And I'm going to get you to talk a little bit about why kombucha is such an interesting system. But can we study kombucha and say, yeah, these are the rules of cooperation that we can program into an LLM?
Well, so my understanding of LLMs, right, is that it's all sort of like a really complicated Markov chain kind of situation where it's like, the likelihood that this thing will come after this thing, and you could have conditional probabilities way down the line, and you can have like all this sort of like syntax probability stuff. That's my understanding of what LLMs are. And like, honestly, I have a hard time wrapping my mind around how you do cooperation in that, because I think a lot of just about like more sort of straightforward decision rules, like, okay, in this situation with these inputs, then I'll cooperate, or with these inputs, I won't cooperate, or I'll gather more information. And I guess you can do that kind of stuff with a LLM, but it is hard for me to wrap my head around how you do that.
Mark, from your perspective, how does this potentially work?
I actually want to address the stochastic parrot comment there.
I thought you might.
So it is true in the technical sense and the least helpful sense that these machines are trained by doing next token prediction, right? Given that this as your input, your precondition, what is the next most probable token, next most probable word in this utterance we're creating here? But that's actually about as helpful for getting an intuition of LLM behavior as noting that for most of my evolution, my ancestors' evolution as a primate, I was hunting and gathering. And so if you look at how evolution conditioned me and my brain and my neocortex, you would never imagine that my species would invent algebraic topology, right? Like there's no way you get from what we did for almost all of human existence. And for sure, algebraic topology. And it's the same is true with LLMs. So yes, it's predicting the next token, but it turns out if you're predicting the next token in a proof of Gödel's theorem, you actually have to understand in some real sense Gödel's theorem to accurately predict the next token. So Jeff Hinton, who's one of the originators of this technology, unapologetically says, yes, these machines think. And that doesn't mean they think the same way we do. It's different. I actually think it's cool that it's different, but they are doing something that resembles cognition. And if you want to take the Dan Dennett approach, it's reasonable to take an intentional stance towards that. If you're interested in understanding the technology. And that actually, getting back to the cooperation piece, when I talk to the AI doomers who think, like, even if I granted that Skynet's going to happen, and I don't think it is, I think that's interesting science fiction, not reality. But even if it did, this thing's smart enough to know game theory, right? If it knows everything about everything, it can compute the Nash equilibrium and say, geez, maybe I don't want to go to war with the several billion of these things that inhabit the planet. Maybe I could cooperate.
Oh, interesting. So actually, I've got to follow that up with you, Athena, because it's the idea that a rational entity comes to the conclusion that cooperation is the better way forward. And what intrigues me here is I know, Athena, you study systems that aren't necessarily intelligent, but they still veer towards cooperation. But you also study intelligent systems in humans. So to what extent is cooperation a way forward which actually sort of aligns with evolution, with natural selection, and yet is mutually beneficial?
Well, first of all, Mark, you've kind of blown my mind with like the idea that the way to think about like the intuition for thinking about large language models shouldn't be just like predicting the next things, but should actually be like this as if intentionality. Like you have to treat it as if it does have goals. So I'm just trying to wrap my head around that. But to answer your question, Andrew, in terms of intelligence, I actually think that we are often a little bit blinded by human exceptionalism, thinking like, oh, we're intelligent and things that are intelligent are so special and can do all these things that other entities can't. But a lot of other entities do computation, right? I mean, cells are doing unbelievable amounts of computation all of the time in this sort of distributed way, and they're expressing genes, and things are turning other things on, and I mean it's a crazy complex distributed computational system, and that's just one cell, right? And our bodies are billions and billions of cells. So there's so much information being processed all the time, just in our bodies, and that the goal of all of that, really evolutionarily, is to make us a functional entity at the level of the organism. So you can get unbelievably complex forms of cooperation happening with nothing that we would call intelligence, I think, in the human exceptional kind of way, just with having fundamentally aligned interests, or largely aligned interests, right, of all of the cells in our body, right? They're on a first pass genetically identical to each other, and their only way forward evolutionarily is through our germline and through the germlines of our relatives and the others that we're interdependent with. So I think there's a huge amount of potential for cooperation to be happening, regardless of the kind of stuff that we're dealing with, if that makes sense.
So there are two things there which actually really jumped out at me. One is this idea of alignment, which I want to get back to in a minute, because I suspect you're thinking of alignment in a different way to how the AI folks think about it, but I actually think there's a lot of sort of convergence there. But the second one, and this is where you blew my mind, talking about sort of computation at the cellular level. So either you can take this or Mark can take it, but I think it's very, very revealing when we think of biology as this hierarchical system where you've got different types of computation at multiple levels. Not all of it would we sort of label with intelligence, but it's all part of a bigger system. And Mark, this feels very much like how you were beginning to describe these networks of LLMs, where maybe one little bit of the circuit or component may not sort of be designated as intelligence, and yet it's still doing stuff. I'm gonna let you run with that, Mark.
All right. Well, I mean, what Athena said was pure fire. You just described, why I do what I do. Why did I become a theoretical computer scientist? Because I believe John Archibald Wheeler when he talks about it from bit, like the universe at its most fundamental level is information. I shouldn't say that declaratively. That's a hypothesis that I happen to believe. Suppose the universe is information, and then all dynamics are just computation, transformation of that information. And what if intelligence is just as Athena said, like pure anthropocentrism and human exceptionalism, like intelligence is amazing because we do it, and intelligence is just a side effect of some particular set of computations, and it's actually not more privileged than other computations, and other computations, it's a computation to fold a protein. It has to be implemented using physics, but it's still, there's a lot of information processing happening there. And so that's actually a pretty complex computation. And so our notions of what's a complex computation, what's an intelligent computation, are so loaded with human folk psychology and folk philosophy that we sort of lose sight of the forest.
Yeah. So Athena, back to you. So this idea of sort of information flow and data, this actually makes a lot of sense to me. Again, going back to biology, to what degree can you begin to understand biological systems in terms of exchanging information, sort of passing information on, sort of growing the sort of the core amount of information we have? And as I'm saying this, I'm thinking about sort of theories around sort of natural selection and sort of passing on genes, but surely that's just about the passage of information.
Yeah, I mean, I think that the frame of, right, like just looking at a lot of biology through this lens of information, it applies at a lot of different levels, from, the transmission of genetic material from generation to generation, to the actual process of, development, right? I mean, as development is unfolding, right? So you're copying cells, right? So in a multicellular organism like us, right? You're making like all these copies of cells, but as they're dividing, their gene expression is changing, and the way that their genes are, expressing is then affecting both the future state of that cell and the states of the cells that are around them. And so you have, like the unfolding of development really is this distributed computational process that's pretty freaking amazing. I mean, it's like it's unbelievable what can be done because each of the cells, you could say that they're identical, but then because of the unfolding of the information, they end up in different states that allow them to, do just unbelievable division of labor and complexification. So yeah, I'd say all of that is because of information flow.
And now bring cooperation back into that, because I mean, again, if you're just looking at biological systems, you're seeing cooperative systems where the level of compute, the level of information transmission is enhanced, I'm guessing, through cooperation between different systems.
Well, it's a feedback loop. So, in order to have the reliable transfer of honest information that's not sort of meant to manipulate the other party, you have to have aligned interests, right? And having genetic identity, right? Like within an organism, that's one way that you can kind of do that. So you can even think of like the signaling systems in our own bodies about how resources flow, right? Those work because all of the parts of our body pretty much have the same interest in making us, get on to the next generation and all of that. But if you have cancer cells, right, that are now genetically distinct, they're on their sort of own evolutionary branch, they actually will evolve to send sort of false signals about saying like, oh, there's a wound here that we need to, fix. Like they will actually like tap into those information flows and send information that manipulates the otherwise extremely cooperative system for the benefit of those entities. And that's a general principle that applies across all of biology. So, John Maynard Smith really is the sort of like, grandfather of signaling theory in evolutionary biology, which is basically, it says you have, senders of information and you have receivers of information, and the information goes through, a medium that can be more or less noisy. And then depending on whether the interests of the two parties are aligned with regard to the sort of topic that the information is about, if you have aligned interests, then you can get honest signaling, you can get honest information flow. But if the interests aren't aligned, then you get sort of these incentives for sending false information that can benefit the sender at the expense of the receiver. So yeah, really, it's like cooperation, information flow, all of this is like, it's kind of all part of the same way of looking at the world.
Mark, so this makes so much sense, but I love this idea, just looking at biology, of sort of honest information flow versus dishonest information flow. And the way, Athena, you're using this idea of alignment, because of course in AI circles, people are talking a lot about alignment. So first question to you, Mark, the way that you and your colleagues, when you're talking AI, talk about alignments, how close is that to what Athena is talking about, or are these night and day different?
It should be closer than it is.
Right.
It's challenging. Some of those talking about alignment are technologists who really haven't thought about social problems and game theoretic problems and cooperation. And so they want a technical solution. Well, I'll just use reinforcement learning with human feedback. But when you sort of step back to the 10,000 foot level, if Jeff Hinton's right, and these things are doing something that looks kind of like cognition and is some form of cognition, probably the best way to align them, we already know, which is how we align humans, which is with correct incentives and structures, right? Like there's governance is a whole field of study. We know how to govern systems. Some approaches are better than others. There's side effects for every different approach we take. You don't always have to love democracy, but ultimately, this is well characterized. And I think we're going to find that as these systems become even more cognitively capable, OpenAI has released a bunch of white papers on super alignment over the last week.
Mm-hmm.
And one of the things they're
and you should say what super alignment is. I mean, what's super about it?
It's Ilya Sutskever's word for alignment. No, so super alignment is aligning super intelligences. So suppose we had an entity, computational entity, that is intellectually superior to a human in whatever way we agree to measure it. So its IQ is 7 million. How do we, with our IQs of 100, align the super intelligent thing? And so one of the things they're constantly looking for in their models is the ability to manipulate the person using the model. Because of course, if I'm a super intelligent AI, I'm going to pretend I'm not, and secretly work towards my own ends.
Yeah. So actually, just on that, and I know the paper that Ilya put out and all the conversations around it, but I think that comes straight back to Athena. So this idea that an organism that's lower down the chain in terms of intelligence, agency, however you want to put it, can somehow manipulate an organism higher up the hierarchy to actually sort of work in ways that benefit the lower down organism. Is this something we actually see in biology?
Oh my gosh, it's all over the place. It's all over the place. Viruses, they get into the nervous system. They change.
So humans are going to become the virus of superintelligence. Is this?
Oh, wow.
I love it.
Turning the tables.
Right.
No, I mean the fact is, like, anytime you have one entity that, rather than sort of like going through all of the trouble of creating the organism or the machine to like do things. So, if you sort of think of it like a virus, right? Rather than even making a cell, let alone an organism, they just get into cells and use the machinery that's there for their own ends, right? And that is all. There's always going to be selection pressures favoring entities that don't go through the trouble of making all the things and just hijack the things that are there.
So then, Mark, I mean, so this sounds perfect, but is this how the AI community are beginning to think about alignment and super alignment? Are they learning from biology, or are they making it up from scratch?
Both things are happening. So the answer is yes.
That's right.
And in defense of the folks approaching this, up until very recently, this was a hugely niche area because funders and colleagues felt like this was so speculative. Okay, maybe we can afford to have 5 people in the world working on this, but it's science fiction. And now all of a sudden it feels acute. And so there's a lot of folks pouring into the field, bringing all sorts of different experiences from technology to policy. And we're in the great sorting out period where we sort of figure out what's the lingua franca, what are the foundational concepts, what are the pillars we're going to build on.
Yeah. So one of the things that's actually bothering me here is if you look at biology, there was a long evolutionary process that led to these hierarchical systems. So it wasn't a bunch of viruses sitting around saying, hey, let's build a superhuman and we're going to control them. It just happened. And I'm guessing it happened because there was an evolutionary advantage to those cooperative systems developing. And yet with AI, we're doing exactly that. We're like the bunch of viruses sitting around saying, hey, let's build a supercomputer, a super intelligence, and we're going to control it. Can we actually do this? I mean, sort of, because this is a completely different route to evolution.
So
I would argue that the pre-training of these large language models, the investment of compute is enormous. Not as much as the blind watchmaker of evolution over millions of years, but a lot. And that's sort of like the evolutionary phase of these particular intelligences, where we sort of start tabula rasa and feed them trillions of tokens and reward good behavior and punish bad behavior. It really has that feel of selective pressure to it.
Yeah. And so, Athena, you were going to jump in.
Oh, well, yeah. So, to kind of go back to the biology, like, absolutely, like the whole process of the evolution of life, like everything happened kind of in the shadow of the threat of getting hijacked, right? So our immune systems are the way they are because if other entities could hijack us, they would. And so, and I mean, this is something that we've seen in, the technological space from the, earliest beginnings of network computers, right? It's like, people trying to hack them, trying to take them over for their own ends too.
But you've just brought in another dimension to this. So yes, we're just talking in a very narrow way about us being able to build super powerful, super intelligent machines, but we control them in that's that relationship. And yet that's just one thread that parallels what happens in nature. Whereas you say you've got these massively complex systems of control and combating control and trying to hijack and take over things. Are we being a little naive if we think we can just take one gazillionth of what happens in nature and build that out and assume everything's going to be great? Or do we need this big picture of what we're trying to do?
Well, I think we do need the big picture. And I also just want to, add that, for the last few minutes, I've been talking about the hijacking thing because I think it's so fun and so cool. But ultimately, the only reason that hijacking of any system is possible is because you have sort of the assumption that there will be entities that are cooperating within what you define as the boundaries of that system. Right. So it's those pathways, those information flows that can get hijacked and taken over. So you need the cooperation there to build something that is worth trying to take over. And also, you don't always need to take it over for your own ends that are against the interests of the entity, right? So you could have aligned interests too. And a lot of microbes that live in and on us actually make us healthier. So, it's not like it always has to be a battle and a war over.
Sure, it can be a win-win. Yeah, but actually you had me at the point where you said that for us to be talking about hijacking, you have to have cooperation in the first place, which Mark, correct me if my thinking is completely off base here, but something that tells me is as we begin to think about future risks from AI, it's important to start from a point of saying where are the positive relationships that we're beginning to develop, because then the risks can be seen in relation to the positive things that we're trying to build out.
Completely agree. So the risks are contextual and relative, and Athena's point is exactly true in all circumstances. It's game theory all the way down. You're going to play Prisoner's Dilemma. You're going to play Prisoner's Dilemma.
Yeah. But to me, just from this conversation, it seems that this is such an important framing and context, from how we think about AI, actually learning from what we already know about complex cooperative systems and beginning to build on that. I did, because I mentioned this earlier, want to get back to kombucha in the last couple of minutes before we finish, because I left that little dangling thread. So, Athena, I'm going to put you on the spot here and ask you not only to talk about why anybody would study kombucha rather than just drink it, but what kombucha can tell us about the future of artificial intelligence.
Oh my gosh. All right. Well, I'll start with the first one. So I started studying kombucha because I was drinking it and it was really expensive. So I was like, why don't I just try to make it myself? So I started making it myself in my kitchen and then was watching it. I'd come home from work and I'd watch it and there are bubbles coming up and things moving. And I was like, what is happening in there? And so I was like, I'm, a researcher. Let me go online and see what papers there are that can tell me what's happening with kombucha. And I found nothing. This was about 10 years ago. There's just nothing. And so I did what any reasonable scientist would do. And I took it into my lab and started studying it in my lab. And really over the course of a few years, discovered that there's a huge amount of cooperation happening just in terms of the way that the bacteria and the yeast are interacting to process the sugars. And they're creating all sorts of cooperative byproducts that actually protect the whole system from being invaded and are probably also storing resources in the SCOBY that are only sort of uniquely extractable by the, entities that are creating it, right? So there's like all this really cool, complex stuff that we're starting to uncover about kombucha. And another, like, and this is where maybe we kind of get into the like AI connection. We're right now exploring the hypothesis that part of what the SCOBY is actually kind of like a collective immune system for the kombucha. And we discovered this, or I'm not going to say we discovered this. We came to this hypothesis sort of accidentally, because when we were doing some other studies, we discovered that if you actually seed the kombucha with just a few sort of outside pathogens, you don't get a very thick SCOBY. But if you put a lot of outside pathogens, and here we're talking about things we just like got from people's hands, so it's not like, super dangerous stuff, just stuff that's on people's hands, that you get a like thick and really healthy looking SCOBY on top, right? And so that seems counterintuitive if you don't have this sort of immune system perspective, right? Like, how could you get this like really, really healthy looking kombucha when you're putting more nasty stuff in? So anyway, so we've been doing some systematic studies, and we're seeing actually that this pattern does hold. The more sort of invaders you put in, the thicker of a sort of collective product you get on the top. So now connecting that to AI.
Do we need a kombucha theory of cooperative AI with everything in there, including the sort of building in the AI immune system?
Yeah, I think so. And so there's some really cool like decentralized dynamics that we think are actually how you get the SCOBY. That when this is my speculation, my hypothesis, we're trying to test it right now, that when you have pathogens that come in, that the microbes that are part of the system will actually kind of enclose them. And as they start to operate cooperatively, they're then creating little sort of bits of the SCOBY that then rise up. And so you actually are getting then selection for this multi-species cooperation when you have these invaders that are doing things they're not supposed to. And then it all kind of coalesces into a big cooperative thing on top. So
the weird thing is, I was just about to say, so that's obviously an evolved system, although I'm not even sure you can extend that, because, I mean, how could an evolved kombucha system work? I guess it's sort of bringing in sort of those traits from other areas. But
humans have been, cultivating it for so long that it actually has evolved through, human intervention.
So I guess
but you also have like general sort of biofilm adaptations potentially.
Right.
Well there. Yeah.
So then to close us out, Mark, I want to come back to you and ask you to sort of riff off of that, because, I mean, yes, it's fun to talk about kombucha, but now we're talking about a complex but still a fairly constrained biological system that shows these sort of emergent properties through cooperation. Is the stuff there that we should seriously be considering learning about AI and how we develop these systems that are not only aligned, but actually sort of going to be more cooperative with humans?
I think what I'm hearing is we have to drop some unaligned AIs in so we get a robust immune response.
So that was what I was beginning to take away. Yeah. So actually, sort of one of the things is that there's potentially here, and this is actually quite serious, a danger that if we're too risk averse, we won't be able to develop those immune systems that allow for a robust AI future.
Yes, and if you listen to the tension between those who want to regulate everything about AI and those who want to open all of the models all the time, that's an argument in favor of open innovation. It is, if you regulate things too heavily, you could accidentally create structures where a handful of groups have all the power and there's none elsewhere. And I think that the real lesson from kombucha is the importance of decentralization and humility in accepting that we can set parameters and we can try to guide evolution, but the evolution of this AI ecosystem, no one can actually see where that's going to go. And that's reality.
I would add that if we can have some sort of mechanism for like the small successes, right, in the AI immune system, right, to be able to coalesce those and to say, okay, like how do we then bring these together to be more effective? That would be a really valuable piece to add.
I like that. The AI kombucha sandbox. I think it's going to become a thing. We're actually going to have to wrap up there. We are out of time, but this, as always, feels like a conversation that could go on a long, long time. And I am definitely going to twist both of your arms to get you back. But thank you so much for that. So that's it for this episode of The Future of Being Human Unplugged. Just a quick reminder that you can rewatch this conversation, and you can also find out about upcoming events on our website at futureofbeinghuman.asu.edu. So that's futureofbeinghuman, all one word, .asu.edu. This is our last episode for this year. We will be back with another series of Unplugged live streams in the spring, where again we'll be exploring the cutting edge of emerging science and technology and how they potentially impact the future in ways that you probably won't find elsewhere. If you want to know anything about the upcoming series and you want to join us, and please do sign up for the Future of Being Human updates at, again, futureofbeinghuman.asu.edu to make sure that you don't miss out. And as we wrap up again, another huge thank you to my guests, Athena Aktipis and Mark Daley. And as we're reaching the end of the year, happy holidays, and thank you so much for joining us.